Hey there, math hoppers! In this video lesson, we'll learn how to graph the tangent and cotangent functions. So let's take a look at the basic tangent graph. This is y equals tangent of x, and clearly it looks different than every other trigonometric graph we have seen so far. It does not look like sine or cosine, and that's because it is not continuous everywhere. There are definite breaks, these vertical asymptotes, throughout the graph of y equals tangent of x. Well, if you remember, when we first learned tangent, we learned that it was a ratio of the opposite side length over the adjacent side length. And eventually we learned it as sine over cosine. And that's the definition that's going to help us understand the graph of tangent. So let's just remember that the tangent of x is equal to the sine of x divided by the cosine of x. And that will help us see why there are all these vertical asymptotes throughout the graph of tangent of x. Because cosine is in the denominator, and because there are places where cosine equals 0, and because we can't divide by 0, we have created values that are undefined for tangent and thus create a vertical asymptote in the graph of tangent. So everywhere cosine is equal to 0, you will see a vertical asymptote within the graph of tangent of x. If we remember, as we go around the unit circle, our points x, y are really cosine and sine values. So the cosine of an angle theta is the x coordinate. Looking at a partial unit circle, let's figure out where cosine is equal to 0. So where is my x coordinate 0? Well, cosine is 0 at pi over 2, or 90 degrees, and so we have a vertical asymptote on the graph at pi over 2. Cosine is also 0 at 3 pi over 2. We have the x coordinate equals 0 at 3 pi over 2, and again we have a vertical asymptote there. Well, remember, tangent is a periodic function. The outputs repeat over and over again at regular intervals. So it should make sense that this pattern is going to repeat and that the cosine of negative pi over 2 is also 0 and the cosine of negative 3 pi over 2 is also 0. So we have asymptotes there. These asymptotes will actually be very, very helpful because they frame our tangent function. They frame one complete cycle of our tangent function. And we're going to see a little later on how helpful that's going to be. First, let's go over some of the properties for tangent of x. Let's talk about the domain. We already talked about it's not all real numbers. There are breaks in this graph. And let's talk about specifically where they are. We see that we have a break at pi over 2. We have a vertical asymptote where x can't be pi over 2. And we have another one at 3 pi over 2. So what is the distance between these two asymptotes? Well, pi over 2 plus 2 pi over 2, or pi, happens to be 3 pi over 2. So the distance in between the asymptotes is pi radians. That gives us a domain of pi over 2 plus or minus k pi. It's basically saying x can be everything except pi over 2 plus or minus any multiple of pi. Because pi over 2 has an asymptote and every pi radians there's another one, we say our domain is x can't be pi over 2 plus or minus k pi. Meaning it can be everything else, right? When we put exclusions in the domain, it means all real numbers except pi over 2 plus or minus multiples of pi. And our range, what's our range? You can see from this graph that we travel up towards positive infinity and down towards negative infinity. So our range is going to be all real numbers, negative infinity to infinity. Let's talk about continuity. We know that the domain is not all real numbers. We know that there are breaks in the graph of tangent of x. When we talk about continuity, we talk about continuous on its domain. And if we look on the domain of tangent of x, so in between the vertical asymptotes, yes, it is continuous on its domain. It is also increasing on each interval in its domain. So we say that it is continuous and increasing on each interval on the domain. Is it symmetric? Well, the shape of us says it might have that point symmetry that odd functions have. So let's see. And yes, it has point symmetry. It has symmetry with the origin, meaning for every point x, y, there's another point negative x, negative y. And that exists here with pi over 4, 1, and negative pi over 4, negative 1. So this is an odd function, not odd meaning weird, but odd in the sense of even and odd functions. And we'll talk more about that in future lessons. Is it bounded or unbounded? Remember, sine and cosine were bounded above and below, but this goes off to infinity and to negative infinity, so this is unbounded. Is there an absolute max or min? There are no absolute maximums or minimums because, again, it is unbounded. Now let's talk about something really important for tangent. It is a vertical stretch, not the vertical shift. This is a stretch of the function, and it is 1. And we're measuring from 0, or from the midline, because 0 is also the midline here, to pi over 4. And why pi over 4? Pi over 4 right over here, because you're looking at the measurement from the 0 and the measurement between the 0 and the asymptote. So in between 0 and the asymptote, you have this distance right here. And that distance is 1. For the parent function tangent of x, that basic vertical stretch is going to be 1. This comes in really important when we're dealing with transformations of tangent functions. For example, if we had y equals 2 times the tangent of x, we would have the same basic shape, but this stretch would take place right here. This point right here would go up to 2, and this point right here would go down to -2. It would be a stretch of the tangent function vertically. A lot of people call it the amplitude, like they did with sine and cosine. But remember, sine and cosine had a max and a min, and that amplitude was very clear to see. It's a little more discrete here with tangent. It's not as obvious a change. You're really just stretching that function. Asymptotes. So we talked about vertical asymptotes. There are no horizontal asymptotes, and vertical asymptotes happen every x equals k times pi over 2 for all odd integers of k, or you could say every pi over 2 plus or minus k pi. It happens at pi over 2 and literally every pi radians to the right and every pi radians to the left. Let's talk about the period. Okay, so we did talk about the distance between these vertical asymptotes being pi radians. And that's exactly what the period's asking. The period says, how long does it take for the tangent function to repeat itself? Or how long does it take to complete one full cycle? And we use the asymptotes to measure. And we can see the period of tangent is pi. From negative pi over 2 to pi over 2, there are pi radians. Okay, so let's look at some values. Remember, tangent can also be thought of. So far we've said opposite over adjacent, sine over cosine, and now we've got y over x. Because remember, sine is y and cosine is x. So a lot of times when you're working with the unit circle and you have x, y coordinates, you think of tangent as y over x. That's the easiest way to do it. So let's make a table of tangent values just pulled from our unit circle, doing y over x for tangent. And we see here we have a pattern. Everywhere sine is 0, that's a numerator in our fraction. So if the numerator is 0, the value is 0. So where sine is 0, tangent is 0. Where cosine is 0, remember we talked about that, that's where the vertical asymptotes are. Tangent is undefined. And we see this pattern, undefined, -1, 0, 1, undefined. So vertical asymptote, -1, 0, 1, vertical asymptote. So let's just sketch the basic function of y equals tangent of x. Even though you've already seen it, let's talk about the steps you'll take when you graph these functions. So the first thing you're going to do is place your asymptotes. So the asymptotes for y equals tangent of x, and I'm going to do a few cycles here. I'm going to say -3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. Those are the values from my table. Next thing you're going to do is place your zeros. Your zeros are going to happen halfway between the asymptotes. Of course, this is tangent. We know where the values of tangent are 0. They're where sine is equal to 0. So I know sine is equal to 0 at -pi, at 0, and at pi. So I place those zeros. But make sure you're noticing that your zeros are halfway between your asymptotes. Okay, the next step. Now, normally, and on the next graphs, I will have pi over 4 and negative pi over 4. But I didn't put them here because I want you to notice a pattern. We are going to place our 1 and -1 halfway between the zeros and the asymptotes in an increasing pattern. Now, granted, I know that you guys know the pi over 4 has a tangent value of 1. But look at the relationship. Look at what's happening. So yes, right here is pi over 4, and I have a tangent value of 1. But it's really halfway between the 0 and the asymptote. So halfway between the 0 and the asymptote, I place a 1. And then halfway between the 0 and the asymptote going to the left, I place my -1. I do that with each cycle of tangent. So here, I might not know what the value is. I mean, we do. It's negative pi over 4. But you go halfway between the 0 and the asymptote, you place your 1. The other side, halfway between the 0 and the asymptote, place your -1. Do it again with the third cycle. And now you can draw your curve on increasing patterns, right? You can draw your curve on each interval, remembering that the tangent graph hugs those asymptotes. So let's graph 1, 2, and 3. And that's it. Because this pattern keeps repeating. This is the pattern that keeps repeating. Asymptote, -1, 0, 1, asymptote. That's how easy tangent is to graph. You plot those asymptotes, you find your zeros midway between, you find that vertical stretch point midway between the zeros and the asymptotes, and you're done. So now let's look at one that actually has some transformations. This is the graph, or this is the equation, y equals 3 times the tangent of x minus pi. So what do we have that's different? We have that vertical stretch by a factor of 3, and we have x minus pi instead of just x. If we remember from all of our other functions, anytime we had something within the parentheses, that was a horizontal shift, and that's going to be the same thing here. So let's look at the basic tangent function, very similar to sine and cosine that we've already learned, but it's y equals a times the tangent bx minus c plus d. And let's talk about all of these variables. A, remember, a was the amplitude for sine and cosine, and some people call it the amplitude. I have a very hard time calling it the amplitude. It is a vertical stretch. Without tangent having a max and min, it's very hard to think of it as an amplitude. It's really stretching the function vertically. B, remember, is the number of cycles that you will normally see in the normal period. So within pi radians, you normally see one complete tangent cycle. Well, B will say this is how many tangent cycles you'll see in the normal period. So if it's 2x, you will see 2 full cycles of tangent where you used to only see 1. All right. Don't confuse B with the period. B is used to find the period. You take the normal period pi, divide by the absolute value of B, that gives you your new period for the function. Because remember, if you're seeing more or less cycles of tangent, that's going to affect how long it takes to see a tangent cycle. If you're seeing less than 1 full cycle of tangent, your period's going to be longer. It's going to take longer. If you're seeing more than 1, your period's going to be shorter. It's going to take less time if you see more than 1 where you used to just see 1. Okay, C. C indicates there's a horizontal shift. We call it a phase shift. And you find that phase shift by doing negative C over B. Remember, we've always done horizontal shifts opposite the sign within the parentheses. We did it with quadratics. We do it with every single function. So it should be fairly reasonable that we're taking negative C over B to find the horizontal shift. And plus D is our vertical shift with the sign, super easy, and it's been like that for every function we've ever learned. Now let's list all the similarities and differences to our parent function. So we have a vertical stretch by a factor of 3, so this is going to be stretched by a factor of 3, and we'll see that. We have a C value, so we have a horizontal transformation, negative C over B, so that's going to be positive pi over 1. So it's just going to be a horizontal transformation plus pi. That means it is shifted pi units to the right. So we see a negative pi right in here. That should tell us, opposite the sign, we're going to move to the right pi units. Remember, it's really pi over 1 because we have to do C over B. But since B is 1, it's just going to move to the right pi units. Okay, so what's the period? We do not have a coefficient of x, so the period remains unchanged. The period is pi. There is nothing added or subtracted to this function, so there is no vertical shift. Now, when I say that this function is shifted pi units to the right, many of you can just move it and plot it pi units. But what we're going to do to make it easier, anytime you have a B or a C value, anytime you have something happening within this parentheses, we are going to find new asymptotes, and we are going to plot the asymptotes and then just use the pattern that we know to draw the curve. It's much easier if you first find your new asymptotes. So to help graph, when there is a phase shift, we're going to say, I know the parent function has asymptotes at negative pi over 2 and pi over 2. So what I'm going to do is take what's in the parentheses. I'm going to take x minus pi and set it equal to negative pi over 2, and x minus pi and set it equal to pi over 2 to find the new asymptotes, right? You take what's changing, set it equal to the old asymptotes, and you get your new asymptotes. So let's use the graph of the tangent of x to find our new function. And I need more room, so let's move everything up. There's all the information we already had. Let's pop the graph of tangent of x up there. So graph of tangent of x, we've been working with it, we've been seeing it. we've got a vertical asymptote at negative pi over 2 and pi over 2. We have a 0 here at 0. We also have those 2 points that are going to help us with our vertical stretch. We have pi over 4, 1 and negative pi over 4, negative 1. And those are all going to help us graph this function. So let's first find our new vertical asymptotes. If we take the right-hand asymptote, we will say, what is the new asymptote? We take what's in the parentheses, x minus pi, right here, x minus pi, set it equal to what the right-hand asymptote normally is, pi over 2. So we add pi to both sides of this equation. So when we add pi, we add 2 pi over 2 technically. So we get x equals 3 pi over 2. That will be our new right-hand asymptote. Let's do the left-hand now. The new left-hand asymptote, we're going to take what's in the parentheses, x minus pi, set it equal to negative pi over 2, because that's where our asymptote started. That was our first, our left-hand asymptote for the parent function. Add pi to both sides. Pi plus negative pi over 2 is positive pi over 2. So x equals pi over 2. That's our new left-hand asymptote. That should make sense because think about this. We went from negative pi over 2 being where it started, and we shifted pi units. Well, what's pi units away from negative pi over 2? It's pi over 2. So now we're going to shift it, and this function's just going to start here. Okay, so what's going to happen with our vertical stretch points? Well, pi over 4, 1 is going to go up to pi over 4, 3. And negative pi over 4, negative 1 is going to go down to negative 3. Okay, so let's graph this, and let's graph both functions on the same graph and see if we can make sense of it. So in purple, we have our y equals tangent of x, which we already had. And this new green function is 3 times the tangent of x minus pi. So what has happened? Our left-hand asymptote is shifted to pi over 2, and then 3 pi over 2. Our 0 is still halfway between there, so our 0 is at pi. And what happened? We have in between, halfway in between pi and the asymptote, so in between pi and 3 pi over 2 is 5 pi over 4. Where our shift would have been at 1, it is up at 1, 2, 3. And then here at 3 pi over 4, we went down to negative 3. So you see those new vertical stretch points, right? So that's why I don't call it an amplitude. It's a much more subtle change than an amplitude change for sine and cosine. Now, remember, our 0 is still halfway between the asymptotes. And we found that fairly easily. So let's go ahead and graph the cotangent function. The basic cotangent function is going to have a lot of similar properties to the tangent function. Of course, it doesn't look exactly the same. It is decreasing over its interval, and our asymptotes are in exactly the same place. Let's think about why. Cotangent is the reciprocal of tangent. So cotangent is equal to cosine over sine. Therefore, you are going to have vertical asymptotes or undefined places for cotangent everywhere sine is equal to 0. So before we had them where cosine was equal to 0 because cosine was in the denominator, can't divide by 0. Sine is in the denominator, we still can't divide by 0. So wherever sine is equal to 0, we're going to have a vertical asymptote. Remember, for our going around the unit circle, x, y is cosine sine. Sine is just your y coordinate. So if we look at our partial unit circle here, where is sine equal to 0? Well, it's equal to 0 at 0, and then again at 2 pi, because remember it starts and ends in the same location. It is 0 again at pi. We have vertical asymptote at 0, vertical asymptote at pi. We would have another one at 2 pi. And remember, this is periodic, so we will have one at negative pi as well. All right, so it's probably easier to see this. But look at what happens here. We have one full cycle of cotangent. It is a decreasing function, unlike tangent. And again, our asymptotes frame this thing out. And look, it goes from 0 to pi. So one complete cycle of cotangent, again, is going to have a distance of pi. It's going to take pi radians to make a complete cycle. All right, let's talk about just a few of the properties of cotangent. The domain, we've already talked about it. It is not all real numbers. We have breaks in this thing. We have vertical asymptotes anywhere sine is equal to 0. So let's see where we have them. We have one at 0, and we have one at pi, and we have one at negative pi. So it appears that the domain is all real values except 0 plus or minus pi, right? From 0, if you go pi in the right direction, there's an asymptote. You go pi again, there'll be another one. If you go pi units to the left, there'll be one there, and another pi, there'll be one there. So our domain is going to be all real numbers except 0 plus or minus k pi, which means 0 plus or minus any multiple of pi. Our range, we can see, is still goes up to infinity and down to negative infinity, so it's still all real numbers. Now this time, we are not increasing. We are decreasing on each interval. So we are decreasing and continuous on each interval. It is again symmetric with the origin. It is an odd function, just like tangent is. And from that shape and looking at that origin, you can kind of tell, yeah, this is going to have that point symmetry. It's going to be just like tangent in that it's an odd function. Let's look at our vertical stretch. Again, looking at from our 0 or from our midline to pi over 4, what is that distance? And that distance, again, is 1. And that will be really helpful when we're graphing transformations of cotangent. Asymptotes. No horizontal asymptotes, but we do have vertical asymptotes every x equals 0 plus or minus k pi. So starting at 0 and every multiple of pi to the right and to the left. Period. How long does it take for cotangent to repeat itself? How long does it take for one full cycle of cotangent to happen? Again, use those asymptotes to measure this. It's very easy to see this one. From 0 to pi is clearly pi radians. So the cotangent of the period of cotangent is pi, just like tangent. Okay, let's quickly look at some values for cotangent. Remember, we're taking them from the unit circle, and it's easier to think of cotangent as x over y. Because when you have your unit circle, you have a bunch of x and y coordinates, so finding cotangent is easier if you just do x divided by y. We have the same pattern that keeps repeating. I mean, not the same exact pattern as tangent, but we have a pattern that keeps repeating. We have asymptote, 1, 0, negative 1, asymptote. This time we start at 1 and we go to negative 1. That gives us our decreasing pattern. The steps we take to graph this will be exactly the same as we did with tangent. We're first going to place our asymptotes. I'm only going to do one cycle, so I'm going to place an asymptote at 0 and at pi. We're going to place our zeros. I, of course, will only place 1 0 at pi over 2. And then we're going to place our 1 and negative 1 halfway between the zeros and the asymptotes in that decreasing pattern. So I'm just going to go ahead and put pi over 4, 1, and 3 pi over 4, negative 1, and then draw our curve in. And remember, it hugs those asymptotes. And that's one cycle of cotangent, and it will repeat forever and ever and ever. Now let's do a transformation of cotangent, and then we can call it a day. So let's graph y equals 2 times the cotangent of x divided by 3. First of all, when you see x divided by 3, let's rewrite this. I don't see a b value here. I want to rewrite this. You know there's a 1 in front of x. So 1x divided by 3 is really 1/3 x. So let's rewrite it so we see that b value. This b value says, hey, where you're used to seeing one full cycle of cotangent, you're only going to see 1/3 of cotangent. That means it's going to take a whole lot longer, 3 times longer to be exact, to see that full cotangent cycle. So let's use our equation. A times cotangent of bx minus c plus d. What values do we have? We have a vertical stretch of 2, so we have an a, and we have a b of 1/3. This tells me I'm only seeing 1/3 of the cotangent graph where I used to see a full one. All right, so A is our vertical stretch. Remember, similar but not really the amplitude. B is the number of complete cycles. We're seeing less than 1. We're seeing 1/3 of a cycle. So our period is going to be changed. We're going to do pi divided by 1/3 to figure out what that period is. Let's list all the similarities and differences to our parent function. Vertical stretch by a factor of 2. We'll see that when we graph it. It'll be very similar to that tangent vertical stretch of 3. Horizontal transformation. There is no horizontal transformation because there's no c value, but it doesn't mean we're not doing anything horizontally. And you'll see what I mean in a minute. The period. Period is not pi. It's not the same because we have a b value. So we have to find the period by saying pi divided by 1/3, which is really pi times 3 over 1, which is 3 pi. This should make sense. You're seeing 1/3 of what you used to see. So it's going to take 3 times as longer, or 3 pi, to see what you used to see. Okay, so horizontally, what are we doing? We have a horizontal stretch by a factor of 3. If you see a 1/3 in here, that's a horizontal stretch by a factor of 3, not by a factor of 1/3. 1/3 is how many cycles you see. The factor that the stretching is happening by is 3. It's taking 3 times longer to see the same cotangent cycle. And of course, again, there is no vertical stretch or vertical shift, not stretch. Okay, so even though there's not a phase shift, we are still going to find new asymptotes. Why are we going to find new asymptotes? Well, because the asymptotes are going to change. If you're only seeing 1/3 of a cycle, we're used to see one. To see a full cycle, which is what we're graphing, it's going to take 3 times longer. So that asymptote on the right side is changing. So to help graph when there's a horizontal stretch, we are going to take exactly what we did. We're going to take everything in the parentheses, like we did for tangent, and we're going to set it equal to the original asymptotes. We're going to set it equal to 0 and pi, the asymptotes of cotangent of x. So let's see what happens. Let's find those asymptotes. Let's get a new graph board because I am running out of room. Let's use that parent function, y equals cotangent of x, to graph 2 times cotangent of 1/3 x. Here's all the information we have. Here's cotangent of x. So cotangent of x, remember we had a nice, neat little graph. We had an asymptote at 0. We had an asymptote at pi. We had a 0 at pi over 2. We had our vertical stretch points, if you want to call them, at pi over 4, 1, and 3 pi over 4, -1. And how is this going to change? Well, that's going to go up to 2. That's going to go down to -2, but it's also going to stretch horizontally. So let's find those new vertical asymptotes first. Vertical asymptote, you're going to take everything in the parentheses and set it equal to the old one. So x over 3 equals 0. Well, if you multiply both sides by 3, you get 0. So the left asymptote stays the same. The right asymptote will not, because remember, we're stretching this sucker. You're only seeing 1/3 of cotangent where you used to see cotangent. So this thing is going to be 3 times as long. So let's set pi over 3 equal to pi. Remember, that's where the old right-hand asymptote was. Multiply both sides by 3, x equals 3 pi. It should make sense that our new asymptotes is 0 and 3 pi. That's 3 times longer than it used to be. And remember, this sucker is getting horizontally stretched by a factor of 3. Why is it getting horizontally stretched? Because it's taking 3 times as long to see one full cycle of cotangent. I feel like I may have said that almost too many times, but it's that important. All right, let's plot them both on the same grid. In purple is cotangent of x. So here's what we used to have. And this way stretched out green function is our new laid back cotangent, right? Because it's taking 3 times as long to do what it used to do. So let's look at it. We still have a 0 at 3 pi over 2. It's still going to be halfway between your asymptotes. I have an asymptote at 0 and an asymptote at 3 pi. So 1.5 pi is halfway between the asymptotes. And then I'm going to take halfway between the 0 and the asymptote to plot my vertical stretch of 2 and -2. And that's my graph. That's it. The vertical stretches. Notice I didn't do any math. I didn't set up an equation. I plotted my 0 halfway between my asymptotes. And then halfway between the asymptote and that 0, I put my 2 and my -2. Because that's where those vertical stretches happen. Halfway between the 0 and the asymptote. All right, that's cotangent and tangent. Still have questions? You know what to do. Subscribe to our YouTube channel. Send them in to us. We'll get something made for you. Until next time, Math Hoppers, take it easy.